In this video, we discuss heat engines. A heat engine is a device that transforms heat, that is energy transfer from a temperature difference, partly into work. I say partly here because we will see that it can never be 100%. A heat engine will take heat from a hot reservoir at a temperature TH and reject heat to a cold reservoir at a temperature T cold and produce some work. Now remember that we chose a convention where the work is done by the system to the surrounding. So for a heat engine, W is positive, the work is positive. And we also use a convention where the heat is added to the system. So QH is positive, but QC is negative since QC is heat rejected to the cold reservoir. So for the engine, the net heat is QH plus QC, which you can write as QH minus absolute value of QC, since QC is negative. Because the engine is running a cycle, at every cycle, it must come back to its initial state. That means that the internal energy at the end of the cycle is the same as the internal energy at the beginning of the cycle. So we can write that delta U is equal to 0. And the first law of thermodynamics says that delta U is Q minus W, so we have QH plus QC minus W is equal to 0. This gives us a relation between the work done by the engine and the heat absorbed and released by the engine. The important aspect here is that there is nothing else than just conservation of energy. Right? Now, ideally, you want the engine to produce the largest amount of work. That means an engine that transforms all of the heat into work and does not reject any heat. So you want W equal to QH and you want QC to be equal to 0. But no heat engine can do that with 100%. Right? And to measure this, we define the thermal efficiency as the ratio of W divided by QH. So if all the heat is converted into work, then W equal QH, and you have 100% efficiency. But if W is smaller than QH, then you have less than 100% efficiency. Since W is equal to QH plus QC, then we can write the thermal efficiency as 1 plus QC over QH. Or since QC is negative, we can write 1 minus absolute value of QC over QH. From this relation, you can see that the more heat is rejected, the less efficient is the heat engine. As an example of a heat engine, we will describe the Otto cycle. First, the first step is the intake stroke. The piston moves down and the fuel will enter into the cylinder. And then there is the compression stroke. The piston moves up and the fuel is compressed. The pressure will increase during this step. And then there is the ignition. Right? The spark plug will ignite the mixture of gasoline and air. And this is the step that will provide heat to the system. Right? It happens during the compression. And then there is the power stroke. Right? The gas expands and the piston moves down. And this is where the mechanical work is produced really. And finally, there is the exhaust stroke. The exhaust valve is opened and the burnt mixture will be released. And this is where some heat is rejected to the outside. Now, the idealized Otto cycle on a PV diagram looks like this. Between point A and B, we have an adiabatic compression. This is the compression stroke. Then between B and C, there is the ignition of the gasoline-air mixture. And this is where the heat is taken in the system. The pressure will increase. Then between C and D, we have the adiabatic expansion. This is when the piston moves down and the volume increases. And this is the power stroke. And then between D and A, the exhaust valve is open and the pressure decreases. This is where some of the heat is rejected. In this idealized cycle, we will have two volumes, V minimum and V maximum, and we will write V maximum as R times V minimum. So R represents the compression ratio. So what is the thermal efficiency of this idealized Otto cycle? We will show that the efficiency E is equal to 1 minus 1 over R to the power gamma minus 1, where R is the compression ratio and gamma is the ratio of heat capacities of the gas mixture in the engine. So how do we show this? One method that you can use is to take every processes and write everything you know about these processes. So here we have two isochoric processes and two adiabatic processes. So let's start with the isochoric processes. We know that for isochoric processes, the work done by the system is zero, right? There is no change of volume. And we know that if the volume is constant, we can calculate the heat added to the system as NCV delta T. And so for the process from B to C, we have QH is equal to NCV TC minus TB. And since TC will be larger than TB, we indeed have QH that is positive, so the heat is added to the system. And for the isochoric process from D to A, we can write QC is equal to NCV TA minus TD. And since TA is lower than TD, then QC is indeed negative, and so heat is rejected by the system. At this point, we can already write an expression for the thermal efficiency. We have seen that the thermal efficiency is equal to 1 plus QC over QH. So that leads to E is equal to 1 plus TA minus TD over TC minus TB. And we don't have the relation that we are looking for yet, but we haven't used anything about the two other processes which are adiabatic. So let's do that. What can we write for an adiabatic process? We have seen that during an adiabatic process on an ideal gas, then we have TV to the power gamma minus 1 is constant during the process. We also have seen another relation with pressure. It's PV to the power gamma is a constant. But here I already have a relation with the temperatures. So let's use the relation that contains the temperature. For the adiabatic compression from A to B, we can then write TA Vmax to the power gamma minus 1 is equal to TB Vmin to the power gamma minus 1. And since Vmax is equal to R Vmin, when R is the compression ratio, then we can replace Vmax to the power gamma minus 1 by R gamma minus 1 times Vmin to the power gamma minus 1. And then we can simplify by the Vmin power gamma minus 1, and we obtain that TA times R to the power gamma minus 1 is equal to TB. So this relation gives you the temperature TB after the adiabatic compression, and you can see that the larger the compression ratio, the larger the temperature increase will be. And we can do the same with the adiabatic expansion from C to D. In this case, we will obtain that TC is equal to TD to the times R to the power gamma minus 1. So we can now combine our expressions for the thermal efficiency and replace TB and TC by the relation in terms of TA and TD. And we obtain that E is equal to 1 plus TA minus TD over TD R to the power gamma minus 1 minus TA R to the power gamma minus 1. And then simplify by TA minus TD, and we obtain the relation that we wanted. So you see that the thermal efficiency for this idealized cycle is smaller than 1. It is not going to be 100% unless the compression ratio is infinite, which is not realistic. A typical compression ratio is about 8. and the gamma for air is about 1.4, and so a typical thermal efficiency is about 56%. So this is well lower, well below the 100%. Right? We are converting only 56% of the heat into mechanical work. So if you're an engineer and you want to increase the thermal efficiency, you see that you need to increase the compression ratio. But if you increase the compression ratio, you see that the temperature TB, which is equal to TA times R to the power gamma minus 1, then TB will increase. And so this could lead to spontaneous explosion of the air-gasoline mixture. And this is also called pre-ignition or auto-ignition, self-ignition, detonation, or knocking. And this is bad for the engine, and you can damage the engine. In fact, when you take gasoline at the gas station, you know that you can choose different octane ratings, 87, 89, 93, and so on. And this number represents the resistance to pre-ignition. So if you have a larger octane rating, then you will have less pre-ignition, so less engine damage. The motor design can use a larger compression ratio, and so it can be more efficient. Now, another way to avoid the problem of self-ignition is to introduce the fuel after the compression. Right? This is the idea of the diesel cycle. In the diesel cycle, the fuel combustion happens at constant pressure. And because the air is already compressed and hot, the fuel ignites spontaneously, and there is no need for spark plugs. And because there is only air, but no fuel during the adiabatic compression, then the compression can be much larger and achieve higher efficiency. Both the Otto cycle and the diesel cycle have a similar exhaust process. There is an example of engine that does not burn fuel and does not need to exhaust gas. And this is the Stirling engine. So in this demo, I have two Stirling engines. They also work with a cold and a hot reservoir. And since I have two of those engines, I'm going to use one with a cold reservoir at a liquid nitrogen temperature. So I will fill a cup with liquid nitrogen. In this case, the hot reservoir will be the room temperature. And I simply place the Stirling engine on top of the cup. So the bottom is the cold reservoir, and the top is the hot reservoir, which is the room. Now, for the other Stirling engine, I will use hot water as a hot reservoir. So this could be a cup of hot coffee or hot tea. So here I'm simply using hot water. And in this case, the cold reservoir will be the room temperature. Then I place the Stirling engine on top of the cup. So I think I have a little too much water in this one. Let me remove some. Okay, so now the bottom is the hot reservoir and the top is the cold reservoir, which is the room. So in both cases, we use the temperature difference to create work. Now, while those engines are getting thermalized, let me illustrate how these engines are working. So in this schematic representation, we have two pistons that create two volumes for the gas. One is in contact with a cold reservoir, and the other one is in contact with a hot reservoir. But the lower piston can let the gas travel from one volume to the other. So at this point in the figure, you see that the contact with the hot surface is larger, and so the gas will warm up and expand. As the gas expands, it will increase its volume by expanding into the cold region. But as this happens, then the contact with the cold surface will increase, the gas will cool down, and then it will contract. And this expansion and contraction is going to result in producing the mechanical work. For example, here, it will rotate a wheel. Now you see that the gas never leaves the engine, so there is no exhaust and there is no explosion taking place, so this is very quiet. The idealized Stirling cycle on a PV diagram looks like this. You have two isothermal processes and two isochoric processes. And now let's come back to the demo. The engines are thermalized and they are ready to start. Right? You just need to give them a little push and then they start. Now, because there is no need for a fuel, they can run forever, right? As long as there is a temperature difference between the top and the bottom. Now, it's quite fascinating to see that you can get so much speed with a simple cup of hot water. Now, one issue with the Stirling engine is that the heat exchange takes time. It is much slower than a combustion engine, so we cannot change the power rapidly. So it's not useful for transportation. If you're at the red light and then you want to start, then we cannot change the power very rapidly. But it is very efficient if you don't need to vary the power. Right? And another thing is the heat source can be anything. So here I used hot water, for example. You can burn something, or you can use solar energy. For example, this power plant in Spain uses a Stirling engine that is positioned at the focal point of a parabolic mirror. As we have seen, if you remember, if you consider the sun as an object located at infinity, then its image in a parabolic mirror will be located at the focal point. So the solar energy focused at the focal point is used as the heat reservoir for a Stirling engine, which is then used to produce electricity. Now, before we conclude, let me mention how this lecture on heat engines is related to the second law of thermodynamics. We will see that one of the results of the second law of thermodynamics can be stated this way. It is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts heat completely into mechanical work with the system ending in the same state in which it started. And this is known as the engine statement of the second law, or the Kelvin-Planck statement of the second law. So for heat engines, this means that it is impossible to have QC equals 0, or that it is impossible to have 100% efficiency.